everyone. Myself, Dr. J. Glory, Associate Professor of Physics, Institute of Aeronautical Engineering. Today, our topic is dual nature of radiation. Here, the topics that we are going to cover is what is radiation, light as a wave, that is a behavior of a wave, and then light as a particle, dual nature of light, and then differences between matter waves and electromagnetic waves. These are the topics that we are covering in this session. So first, we go to the what is radiation. So radiation means what? So radiation is the emission of energy. Radiation means the emission of energy as an electromagnetic wave. So here the term electromagnetic wave. So what is electromagnetic wave? What is electromagnetic wave? Electromagnetic wave is a wave in which electric fields and magnetic fields that are perpendicular to each other. So in electromagnetic waves that are produced, the wave is produced due to the electric field and magnetic field which are oscillating together. So that by oscillating electric field and magnetic field together produces electromagnetic wave which is perpendicular to both. So in this figure, the electric field in y direction and the magnetic field is in z direction. So these perpendicular electric field and magnetic field are oscillating together. This is regarding to the electric field. The wave, that is the oscillation of the wave, is regarding to the electric field, and the yellow, this is magnetic field. So the oscillations of electric field and magnetic field together produces electromagnetic wave. And the term here, emission of energy. So here the emission of energy could be done in two ways. Two ways. That is, the emission of energy could be done in the form of particles or packets. And it could also be done in the form of waves. So the emission of energy could be done in two forms, that is, one is particles or packets. Packets means that a small unit of energy. So the emission of energy could be done in the form of particles or packets, and it could also be done in the form of waves. Here we can see that electromagnetic spectrum. While talking about the electromagnetic wave, we have to know that where these electromagnetic waves are around us. So the electromagnetic spectrum tells the penetration of its atmosphere. So here the electromagnetic spectrum with the radiation type, with the wavelength range, and also approximation scale of wavelength here, and could be shown that frequency range. So here 4 different frequencies have been mentioned, and the radiation type, this is radio frequency, that is a radio type wavelength which is in meters 10 power 3, and microwave 10 power minus 2 meters, infrared 10 power minus 5 meters, and this is of visible region, that is 0.5 into 10 power minus 6, and ultraviolet 10 power minus 8, this ultraviolet which is coming from the sun, and X-rays 10 power minus 10, which we use mainly in medical field, and gamma rays, so 10 power minus 12 meters. So related to the penetration of our Earth's atmosphere, these are the ranges. So, and also could be able to see the temperature of objects at which this radiation is the most intense wavelength emitted. We move to the light behaves as a wave. As we talk about the dual nature of radiation, first we have seen that what is radiation. So in that radiation, there is two ways of emissions. That is maybe it in the form of particles or packets, and also it could be done in the form of wave. So first we see that light behaves as a wave. Light behaves as a wave. A wave is spread out over a relatively large region of space. A wave is spread out over a relatively large region of space. It cannot be said to be located just here and there. It cannot be said to be located just here and there, and it is hard to think of mass being located or being associated with a wave. So we couldn't assume that if a particle having mass m that is associated with a wave, we couldn't assume. So that it is hard to think of mass being associated with a wave. So that actually a wave is nothing but a rather spread out disturbance. Simply we can call it as a disturbance in a medium called as a wave. So what are the specifications of a wave? What are the specifications of a wave? So when coming to the specification of wave, it should have a frequency. It should have frequency, mu, wavelength, lambda, and phase of wave velocity, v, amplitude, a, intensity, I. So if a wave have these features, then we said that's a wave. So these are the specifications of a wave. Next we move to the light behaves as a wave. Light behaves as a wave. So in wave theory of electromagnetic radiation, it explained the phenomena of interference, diffraction, and polarization. In wave theory of electromagnetic radiation, it explained about the phenomena of interference, diffraction, and polarization. This radiation, including visible light, infrared, ultraviolet, X-rays, etc. So as we saw in the electromagnetic spectrum, these all the regions are involved. So radiations including visible light, infrared region, light, ultraviolet, and then X-rays, etc. behaves as waves in experiments based on interference, diffraction, etc. So in these radiations, they behaves as a wave in experiments based on interference, diffraction, etc. So this is due to the fact that these phenomena require the presence of two waves at the same position at the same time. So this is due to the fact that these phenomena require the presence of two waves. So that presence of two waves are at the same position at the same time. At the same position at the same time. But obviously, it is difficult for the two particles to occupy the same position at the same time. So thus, we conclude that radiation behaves like a wave. So here what we are telling is radiation including visible light, infrared, ultraviolet, X-rays, etc. behaves as wave. So these are based on the experiments that done on interference, diffraction, etc. So this is due to the fact that these phenomena require the presence of two waves. The presence of two waves at the same position at the same time. When we talk about the interference, so the interference is the distribution of intensity, or else we can say that the modification of intensity in the region of superposition is called interference. The modification of intensity in the region of superposition is called interference. So there we have to modify the intensity distribution, means that we have to take two ways. So let we take a wave, and this wave is x, and also I'm taking the another wave, this is y. So the intensity distribution of these waves, so the modification of intensity distribution so could be different. So the resultant intensity may be like this. So means that the resultant intensity of these two individual waves gives that, suppose x dash. So this resultant intensity may be high or it may be low. So here we are taking two waves. We are taking two waves. So when we are talking about this interference, when we are talking about the interference, the intensity distribution modification, the intensity distribution modification in the superposition region is called the interference. So here we are taking two waves and we are taking the resultant wave. So here in this diffraction also, so according to the Huygens, each wavefront acts as a secondary source for the secondary wavelet. Each wavefront acts as a source of secondary wavelet. So here also we are taking two waves and they are at the same position at the same time. But when we think about the particles, so particles have mass, velocity, and then it should have a momentum. So like that. So it is hard to think about the two particles being in the same position at the same time. So when we are talking about the particles, so it is difficult to think about the two particles occupying the same position at the same time. So thus we conclude that radiations behave like a wave. So light behaves as a particle. So a particle has mass and it is located at some definite point. It should also have some definite point. It can move from one place to another. So a particle has mass and it has some certain position and it can move from one place to another. So thus, the particle is specified by mass m, velocity v, momentum p, energy E, etc. Okay, so the specification of the particle is mass, velocity, momentum, energy, and etc. Suppose when a particle with mass m1 moving with velocity v and hits another particle which is at stationary having mass m2. So the another particle is at stationary and the particle's mass is m2. So the moving particle transfers its kinetic energy and momentum to the other particle. So here a particle having mass m1 with velocity v, it is moving and hits the another particle which is having m2 mass and it is at rest position. It is at rest position. So when the first particle hits the second, so the first particle, that is moving particle, transfers its kinetic energy and momentum to the other particle. So as a result, what happens? The first particle be stopped and the second particle starts to move. So as a result, the first particle stopped and the second coming to motion. So from this, we learn during collision, particle transfers kinetic energy and momentum. Suppose here we shall see through the diagram. So this is a particle. So taking as particle X. This particle have mass m1 and it is moving with velocity v. And there is another particle having mass m2 and it is at rest position. So velocity is 0. So this is a particle Y. So this is in the motion, but it is this particle in stationary rest position. It is in the rest position. So when the first particle X hits the second particle Y, which is at stationary, so it stopped and it starts moving. So how it starts moving? How it starts moving? Because the kinetic energy of the first particle, momentum, is transferred to the second particle. So the first particle, while moving, it has kinetic energy and momentum. So when hits the second particle, what happens? The first particle transfers its kinetic energy and momentum to the second particle. So this first particle stopped and the second particle, by gaining this kinetic energy and momentum from the first particle, it starts moving. So from this, we learn during collision, particle transfers kinetic and momentum, kinetic energy and momentum. Likewise, in the experiment of photoelectric effect, when photons hits the electrons of the metal, it transfers kinetic energy and momentum to the electron. So it results ejection of electrons called as photoelectrons. So that photons of light acts like a particle. So here we are telling about the experiment of photoelectric effect. So in the previous session, we talked about briefly about the photoelectric effect. So in that photoelectric effect experiment, when photons hits the electrons of the metal, it transfers kinetic energy and momentum of the electron. Likewise, we discussed in the previous slide the particles, how they change their kinetic energy and momentum to the other particle. So suppose, let me draw that for understanding purpose. This is a metal, and in this electrons are there. So more number of atoms are there. In that atoms, electrons are revolving around the nucleus in different orbits. So there is occupying of electrons in the valency level. So they, when they hit the, or when they gain the energy, they would detach from the atom, that is they come out from the outermost orbit. So here this is a metal and there is more number of atoms. So when the photon so photons hits the atom, so the outermost orbit electrons, that is valency electrons, get be detached. How they get detached from this atom? That is the energy, the kinetic energy and momentum of this photon. The kinetic energy and momentum of this photon is transferred to this electron, so that the electron gains the energy from the photon, so that they eject the electrons. Likewise, we saw in the previous slide, that is the particles, how they transfer the kinetic energy and momentum to the other particle. Likewise, so photon hits the electron, so the electron gains photon's kinetic energy and momentum, and it detach from the atom and come out. So resulted ejection of electrons. So the emitted electrons are called as a photoelectron. So that photons of light acts like a particle. Photons of light acts as a particle. So coming to the dual nature of light. So dual nature of light or dual nature of radiation, and also we call it as a wave particle nature. So many ways we can call this as this topic. Okay. So dual nature of light. So the phenomena like interference, diffraction, polarization of light, etc. are explained on the basis of wave nature of light. So These are explained on the basis of wave nature of light. So the phenomena, interference, diffraction, polarization of light, etc., could be explained on the basis of wave nature of light. So on the other hand, photoelectric effect, Compton effect, etc., are explained on the basis of particle nature of light. So one is explained on the basis of wave nature of light and the other on the basis of particle nature of light. So thus the radiation has dual nature. So what are the radiation having dual nature? So one is wave nature, the second one is particle nature. Wave nature and particle nature. So both wave and particle. Both wave and particle. To explain the phenomena which involves both particle and wave nature, we use Planck's quantum theory. So to explain this phenomena, that is the phenomena which is we are talking about both particle and wave nature. So we use Planck's quantum theory. So this Planck's quantum theory comes from the after 1900. So before that, there existed theories. We are using classical theory. So in that classical theory, so we explained about the macroscopic particles and all. But here we use Planck's quantum theory to explain dual nature of light. So according to the quantum theory, the emission of radiation will be in the form of photons. According to the quantum theory, the emission of radiation will be in the form of photons. So a photon has a velocity and mass in motion. So thus it has momentum and energy. So that means a photon behaves as a particle. So the energy of a photon is E is equals to h nu. E is equals to h nu, where is the energy of the photon. Nu is the frequency of the radiation. Nu is the frequency of radiation. So along with this frequency, the other parameters also be attributed a wave nature to photon. So along with the frequency, the other parameter attribute a wave nature to photon. That is, photon has dual nature of behaving. That is particle as well as wave. Particle as well as wave. So the concept of dual nature of radiation provoked by de Broglie to suggest the idea of matter waves. So this concept of dual nature of radiation provoked de Broglie to suggest the idea of matter waves. That is, particles like electrons, proton, neutron, atom or molecule have an associated wave with them. So what are the differences between the matter waves and electromagnetic waves? Matter waves and electromagnetic waves. So the matter waves are associated with moving particles. Matter waves are associated with moving particles. So that particles may be charged or it may be uncharged. Matter waves are associated with moving particles. Either it may be charged or it may be uncharged. And the wavelength depends on the mass of the particle and its velocity. Wavelength depends on the mass of the particle and its velocity. So wavelength depends on the mass of the particle and its velocity. Matter waves can travel with a velocity which is greater than the velocity of light. Matter waves can travel with a velocity which is greater than the velocity of light. So matter wave is not electromagnetic wave. As we saw, electromagnetic waves. What is electromagnetic waves? And where they are existing. Here, a matter wave is not electromagnetic wave. Matter wave require medium for propagate. Matter wave require medium for propagate. So they cannot travel through vacuum. They cannot travel through vacuum. So these are the properties of matter waves. Coming to the electromagnetic waves. So electromagnetic waves are produced only by accelerating charged particles. Accelerating or accelerated charged particles. So electromagnetic waves, so are also sometimes also we call it as EM waves. Electromagnetic waves also in shortcut called as EM waves. So electromagnetic waves produced only by accelerated charged particles. The wavelength depends on the energy of the photon. Here, the wavelength in this electromagnetic waves, the wavelength depends on the energy of the photon. But where in the case of matter waves, the wavelength depends on the mass of the particle and its velocity. So wavelength in the matter waves depends on the mass of the particle and its velocity. So in the case of electromagnetic waves, the wavelength depends upon the energy of the photon. Energy of the photon. Electromagnetic waves travel with velocity of light. So what is the velocity of light? C is equals to 3 into 10 power 8 meter per second. So electromagnetic waves travel with velocity of light. So here electric field and magnetic field oscillate together and produces electromagnetic waves. So electric field and magnetic field oscillate perpendicular to each other so that the electromagnetic wave is producing. Electromagnetic wave do not require any medium for its propagation. Electromagnetic waves do not require any medium for propagation. So that is they can travel through vacuum. They can travel through vacuum. So here, while we are taking UV rays and also they don't need to travel medium. So as they are coming from the sun, so that they do not require any medium for its propagation. So that is, they can travel through vacuum. They can travel through vacuum. So these are the topics. These are the things we discussed in this session. Let's see overall view of this session's topic. We just covered what is radiation. Radiation is the emission of energy. Radiation is emission of energy as electromagnetic waves. So that emission, maybe it could be done in the form of packets or it could be done also be in the form of waves. And we went electromagnetic spectrum and the range of their wavelengths and frequencies and where they exist in the Earth's atmosphere. And we went and we saw that light behaves as a wave. So what are the specification of a wave and what is wave mainly. So what is a wave mainly, and then what are the specifications of a wave, and then so what are the existed theories that explained on the basis of different experiments explained about this wave. So different theories explained that light has wave nature. And we saw that light behaves as a particle. So what is a particle and where it exists, and what are the specification of a particle, and when the two particles interact with each other while moving, while they are in motion, how their energy is transferred, and dual nature of light. So in this dual nature of light, so some phenomena explained, some phenomena, interference, diffraction, polarizations explained on the basis of wave nature. On the other hand, the photoelectric effect, Compton effect, etc., explained on the basis of particle nature. So from this, it can be said it has radiation has dual nature. So that is, dual nature is both particle and wave nature. So to explain this dual property, that wave nature and particle nature, we use Planck's quantum theory. Okay, what the Planck's quantum theory tells? So according to the quantum theory, the emission of radiation will be in the form of photons. So that photon have the velocity and also mass in motion, so that it has momentum and energy. So photon behaves as a particle. And what is the energy of the photon? E is equals to h nu. So along with the frequency, there is other parameter which attributes to a wave nature. So photon has dual nature of behavior. So particle as well as wave. So the concept of dual nature of radiation provoked by the de Broglie to suggest idea of matter waves. So that is, particle like electron, proton, neutron, atoms have an associated wave with them. So, and we saw that differences between the matter waves and electromagnetic waves. So here the matter waves are associated with either it may be charged particles or it may be uncharged particles, but they are in the motion. And here the matter waves wavelength depends upon the mass and velocity of the particle. And matter waves can travel with a velocity greater than the velocity of light. And these waves are not electromagnetic waves. These waves are not electromagnetic waves. And these matter waves do not require, these matter waves require medium to propagate. They do not travel through vacuum. So electromagnetic waves produced only by accelerated charged particles. Electromagnetic wavelengths depends on the energy of the photon. And electromagnetic waves travels with the velocity of light. So that velocity of light is c is equals to 3 into 10 power 8 meter per second. And electric field and magnetic field oscillate perpendicular to each other, produces electromagnetic field. So electromagnetic wave do not require any medium to propagate. So electromagnetic waves do not require any medium for its propagation, so that they can travel through vacuum. So these are all the topics we covered in this dual nature of radiation, and also we called it as a wave particle nature of wave particle nature. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.